me share my screen and get started here. As always, we have a lot to cover. Right, so let's get going. The title of the webinar here is Multi-Cluster Kubernetes and Service Mesh Patterns. Now, there's a lot of stuff that we're going to cover here, and I'm hoping to do it justice because this is something that I've been really interested in. It's something that we work with our customers at Solo on, and there's a lot of areas where we can improve people's understanding of how and why you might do this and how it works. So again, my name is Christian. I've been involved in building large-scale distributed systems for quite a long time now. Particularly excited within the last 5-6 years because of the open source that has emerged to enable building these systems in a cloud way, the way that the big clouds like Amazon and Google and Facebook and so forth have been building their systems for even longer, right? 10 years, 12 years. And a lot of this open source is enabling others to adopt and build on top of it to build application architectures that are well suited to go faster, deliver more value, and so forth. Now, I've been involved with Istio and the service mesh community for probably the last 3 years, and I've written a few books on these topics. I also actively do blog on these topics as well. And like I said, there's a lot to cover here. And what I'm considering doing and will likely do is put together all these thoughts into a little bit more cohesive blog, that maybe a series of entries that I go into more detail than I could possibly go in a single hour here. So just kind of summarizing and setting the stage for some of the challenges that we see organizations when they adopt a microservices style architecture or new infrastructure and so forth. They're focused on how do they ultimately improve the outcomes that they desire, which is get changes out, get new features out to production faster and safer so that they can determine whether those new features and products deliver the value that they were expecting. So they want to go fast, they want to experiment, they want to get things out. You've probably heard the term fail fast and so forth. They struggle because every organization is different. They struggle with what's the right processes and patterns to put in place that make sense for them. And in the past, what I've noticed and they've noticed is that building parts of the capabilities within the organization as silos and highly centralized teams, as well as the infrastructure and the technology to do that, and they both influence each other, has contributed to slowing things down ultimately. And what we are challenged with is how do we build the right architectures with the right amount of decentralization to reduce those bottlenecks and contention points so that teams can move faster, but have the right balance of centralized operations, because you still need that. Along with these new, architectures, as well as moving to public cloud and so forth, there's always that question of, well, how do we stay secure, or how do we improve our security while doing this? And of course, some of the big financial institutions, insurance, even retail and so forth, they have to deal with compliance and regulations and separation of data, and certain data needs to be treated differently, like credit card numbers, social security numbers, those types of things. And so our architectures, although they can be new and based on some of the things we see the cloud vendors do, they still have to solve for these problems. And one of the trends that is not new anymore, but at least before Solo I was at Red Hat, and we were kind of at the I was working on Kubernetes stuff before 1.0 of Kubernetes, but then Red Hat unveiled OpenShift, and in an effort to solve these types of tenancy problems, compliance problems, and networking problems, they ended up going down the path of building OpenShift as intended to be large deployments of OpenShift with tenancy baked into it and so forth. But I think the trend now is to put make those boundaries a little bit more explicit and use more clusters, smaller clusters, but use more of them to achieve this level of isolation, this level of compliance, putting certain clusters in certain networks that might be isolated from each other, achieve high availability and scale. So these are kind of the forces. These are the trends that we see in the market right now with Kubernetes, right? Now, when you start to deploy more of these smaller clusters, they may take various shapes. And what I mean by that is you may use multiple clusters to give you high availability. And you may want each cluster to look exactly the same and deploy the same services, have the same network policies, the same ingress routing, and so forth. And like I said, this would help solve out, let's scale out so that we can take more load. Let's create more of these clusters that look the same, so that if one goes down, we have availability. But there might take other shapes also, right? There might be completely non-uniform deployments. They might be owned by separate teams. They might have separate administrative domains. These might be segmented by network. Maybe you put a cluster out in your DMZ, and that's handling any of the incoming internet traffic. And you separate out any of the fleets in your private network. So once you start going down the path of multiple clusters, first of all, things get challenging. You have to manage this somehow. When things are not exactly the same, that can potentially get difficult. And we might want to take pieces of each of those clusters and kind of stitch them together and make it look like it's just one large cluster. We might want to do something like federation. We might have independent clusters. Each team owns their clusters, so they're deploying it to it. But for some services, maybe shared services, they need to be treated as though it's one holistic service across any of these clusters. And so there are examples of that today for Kubernetes. There's quite a few vendors that are working on this problem. Actually, we just did a webinar a couple weeks ago with Weaveworks, which is working to solve this problem. There's also open source projects and initiatives within Kubernetes to help solve this. One of them is called Kubefed, Kube Federation, which basically allows you from a central point to manage the federated pieces between multiple clusters. Now, you can go as far as to say every cluster should look exactly the same, and we can use Kubefed or something like it to make homogeneous clusters. But you could also say, well, just for certain pieces, I want to share configuration. I want particular cluster or a particular application to appear exactly the same on all of the clusters. Now, Kubefed is basically an extension of Kubernetes. They use CRDs to specify what resources should be federated. And they use a management plane, or in the Kubefed literature, they call it a control plane, but it manages multiple of these Kubernetes clusters. Each of the Kubernetes clusters obviously has its own control plane. So the Kubefed management plane watches these federated resources and then applies them to the different clusters under its umbrella. A federated resource using Kubefed looks something similar to this. the name of the CRD is federated service or federated deployment or federated namespace. And you can specify onto which clusters that resource should go. And then the actual spec is exactly the same as the service, as though you would write it without it being for federation. All right, so let's just take a quick look to get a feel for what it's like to use and interact with a management plane to drive the behavior of multiple clusters, because this is a pattern that we will see when we start talking about federation and cross-cluster problems that we're trying to solve. So let's come over here real quick. We're going to do a very simple federation demo. If we look at the federation management plane and ask it what types can we federate across clusters right now, we see by default we have some of the out-of-the-box Kubernetes resources. We can also add our own CRDs, our custom APIs, to this list, and we can federate those as well. What we're going to start off with is federating a namespace, and then we'll federate some deployments into it across multiple clusters. So if we use the kubefed command, there are a few different things for adding new types and federating resources. In this case, we're going to pass it the namespace and ask it to convert it to a federated equivalent, and you can see it created this federated namespace object, similar to what I showed in the slides. So let's actually apply this. Actually, first we're creating the namespace in the management plane cluster, because we're going to store the federated resources into that namespace on the management plane cluster. So we did that. Now, if we look at cluster 1, which has the management plane, we see that the test namespace we just created is there. If we look at cluster 2, which is under our management, we don't have test namespace there. So let's do the same thing, but actually apply it. We're going to create this federated namespace resource. And what we should see is that the Kubefed now creates the test namespace in cluster 2. And so now that's all good and well. Let's take a look at doing the same thing for a deployment. In this deployment, we're passing it to kubefed federate, and it's giving us back the equivalent federated deployment. And what we're going to do is deploy that to our Kubefed management plane. So we see that gets created, the deployment got created. Let's also do the same thing for a service. So we created a federated service and a federated deployment. These deployments and services should now appear in the clusters that we've specified, and we didn't specify any selector, so it should appear in all of them that we specified. So if we take a look at the status of this federated deployment, we can see that it is in a good state. It has been propagated to the various clusters, and the clusters under management are clusters 1 and 2. So now if we do get service in cluster 2, we see the Echo Server service is indeed running in cluster 2. If we look at the pods on cluster 1, we see that the deployment has been deployed there successfully. It's running as well as in cluster 2. So from a single management plane, we have some operational control to help us federate some of the deployment, some of the services, some of the configuration that we might have across multiple Kubernetes clusters. So that's good. We're able to get applications out across multiple clusters. They may be treated as, like I said, uniform, homogeneous clusters, or they may be treated as independent and autonomous clusters. And we're able to get our deployments out and federate them using Kubernetes, which is great. But now the services, they need to talk with each other. they need to communicate with each other, whether that's peer services or databases or message queues or caches or whatever, right? There's going to be traffic going over the network. Now, getting between clusters is not as trivial of a situation as this diagram makes it seem. There are a few patterns that emerge, though. One of them is the most straightforward if you can do it within the constraints of your organization, and that is just treat the clusters and their workloads as though they were just on the same network. That way, when a service tries to talk with another service that exists on a different cluster, the flat networking in there, the routability between the clusters allows that to happen. So that's, as long as they don't collide their IP addresses, and as long as I said the routability is available between those clusters, then this is a perfectly fine scenario. Another option is, instead of being able to route directly to a service running another cluster, you might expose a service running in the remote cluster to everyone. And in this scenario, maybe we have the products service running in a remote cluster. We might expose this as a Kubernetes service, maybe as a load balancer. So in a public cloud, this would create a new load balancer, which exposes this service. And now any of the services in cluster one can talk directly to the load balancer, which ends up routing to the actual service. Now, this doesn't have to be load balancer. This could be node port. This could be host networking. So exposing them on the from the Kubernetes cluster, I guess, is the pattern, right? Now, there's drawbacks to doing this. So, especially on a public cloud, if you're just going to expose every single service that you create, you might have hundreds of thousands of them. That's going to create a lot of load balancers, and those load balancers are not cheap. So, and then other things, like if you were to do node port or host networking or something like that, now you have the operational overhead of trying to figure out, so you don't have conflicting ports, different versions of a service on different ports, and that the port mapping stuff can get kind of messy. Another pattern is to expose the services in a different cluster through a single point, ingress point. So now account, when he wants to talk to products, will talk to the gateway on cluster 2. And then cluster 2 says, oh, you want to talk to products? I know how to route to cluster 2. So now it kind of alleviates the need for having an explosion in load balancers, having to all the bookkeeping and accounting around port mapping, all that stuff kind of goes away. And you have a nice, well-defined entry point into your cluster for any traffic, including cross-cluster traffic. And so this is a common way to do communication between these clusters, multiple clusters. Ultimately, the forces that we need to balance out are, we need the communication between these applications, and especially between these clusters, to be secure. Ideally, we would be able to encrypt the traffic. We would be able to propagate identity between the service communication. When a service, in this case, account wants to talk to a service called history, account is going to have to know how or where this history service exists. What do I talk to? It will need to solve, or the system will need to solve, for service discovery, and be tolerant in terms of failures and changes to the topology. We also need to be able to understand what traffic is flowing across these networks and between these services. And of course, we're going to be we're going to have to deal with the realities of separate networks, whether you have your on-premises networks and your public cloud networks versus on-premises. Maybe you have a DMZ and private network, or even between two Kubernetes clusters, you may have set it up so that they use the same IP space and that are not routable between each other, right? So there's separate Kubernetes clusters and separate networks for them. We have to keep in mind that when we start building our solution for communication here, that we have these multiple clusters, we want to keep our fault domains as isolated as we can. So if things start failing, that doesn't propagate and start taking everything down. And lastly, if we're going to adopt this multi-cluster approach in some of these patterns, then we want to make sure that we don't inadvertently limit ourselves to scale. So if we add more clusters, we're getting, you know, a scaling variable along an axis that it doesn't start to go down. So could you build these patterns just using Kubernetes? And the answer is yes. Kubernetes does take care of a lot of this stuff for you. But once you start to dig into the details, you realize, well, my applications are going to have to do this. The applications are going to have to be aware of what service discovery means across multiple clusters. The applications are going to have to encrypt the traffic between services. The applications are going to have to know how to do client-side load balancing and failover and so forth. And you know, if you're in a position to do that, then go for it, right? On the other hand, that's exactly the problem that the service mesh was built to solve. And specifically what that means is when traffic flows between services, the service mesh can, independently of language or framework that you use to build your application, can do things like client-side load balancing and service discovery and securing the channel and so forth. Right, so the service mesh was built specifically to solve that problem, but now what we want to make sure that we're able to do is solve that problem across multiple clusters, across separate networks, and keeping our fault domains intact. We don't want to inadvertently blend those. So service mesh can help. We see an example of a few different service mesh. The interesting point, though, is that, at least the ones I showed on the previous slide and quite a few others, Envoy is the building block on which these service meshes derive their power. Envoy is the magic behind these service meshes. So Envoy Proxy implements things like zone-aware routing, like circuit breaking, like timeouts and retries, TLS origination and termination, telemetry collection and exposure to other metrics collection databases and systems. And so Envoy plays a very critical role in both service-to-service communication, as well as what happens when you start to scale out to multiple clusters and you have to deal with these challenges of distinct networking, you know, keeping your failure domains small, and traffic routing and failover and these types of things. So Envoy in a service mesh sits next to the workload. And the workload, in this case, account service, when account service wants to talk out to the network, the traffic flows through Envoy. And Envoy can be seen as an interceptor. It's called a sidecar in this deployment model, especially in Kubernetes. It can be seen as an interceptor, which then enriches the network traffic, the application network traffic, with things like client-side load balancing, TLS origination, circuit breaking, and so forth. right? So now Envoy as the backbone of the communications channel in a multi-cluster network or multi-cluster deployment could look something like this, where maybe we have two different clusters, and for them to communicate with each other in a service mesh, they're already talking through this sidecar. And now to cross clusters, there needs to be an intelligent way to expose the services through a gateway and do the translation so that when traffic arrives to that gateway, it gets translated to the correct service. And then of course, for the caller to be able to find that service, whether that's local or whether it's on the gateway or whether it's on n different number of clusters. So we have a service discovery problem here. So key features. So I mentioned things like timeouts and retries, client-side load balancing and so forth. But there's a handful of, and there's more than just on this list, but there's a handful of key Envoy features that greatly enable the fidelity of handling our requests and our traffic in a scenario when applications start to degrade, networks start to degrade, clusters start to fail, and how an application is smart enough to deal with those scenarios. And like I said, Envoy is the core of many of these service meshes. These service meshes don't necessarily expose all of these features, at least yet. So there might be some extra administrative work to get this just right in your environment. But it's still, if you're going to adopt a service mesh built on Envoy, you have to understand Envoy. And so it's a key part of bringing this up in the webinar here. So Envoy can do things like request hedging. So let's go through some of these. Request hedging, request racing. And what that means is if a account tries to talk to another service and that other service starts to misbehave, maybe it's taking too long. Maybe it's overloaded with something else, it's taking too long. Envoy can notice that on a timeout event, the Envoy can automatically retry to a different endpoint in that cluster. And the request racing or hedging part of the description here is whatever happens, whichever of those two calls returns first will be the response that gets returned to the caller. So in this scenario, we're hedging our bet that, hey, this thing timed out, it might not return. Let's quickly call out to something else and see if that returns faster. If it does, let's return the response. And hence the name racing as well. So when things start to look badly, Envoy can respond by hedging its bet. Another thing that Envoy can do is Envoy can do zone-aware routing. So when you start up the proxy, you can say, hey, it's in this zone. And Envoy can keep track of that information. And when it tries to call out to services, collaborator services or account tries to call some other workload, and it starts to notice that the pool of upstream services are becoming unhealthy and probably can't take that the traffic that it's sending in its own zone, will then spill over to a different zone. And Envoy will make this decision. Envoy knows where the pool size and where they are, and will make this decision on its own. But you can be a little bit smarter about that. In what Envoy has called locality aware and weighted load balancing, instead of allowing Envoy to just make the decision of these different zones and when traffic should start routing to cross zones, we can explicitly give them weights when we propagate that service discovery information from the control plane. So Envoy always has a control plane, And in a service mesh case, it's the service mesh control plane. In an edge gateway case, for example, like glue that we have at Solo, that would be the glue control plane. But we can propagate the information about these different endpoints and give them locality metadata and give them weights, so that Envoy will use the services with a locality first, that the locality that's in their zone first, and then start to spill over to other zones as necessary. There's another level of choosing which endpoint to send traffic to, and that's defined in Envoy as priorities, and that comes into play here. But I'll leave that as an exercise for the listener here. The last one that I'll cover is aggregate clusters. So when Envoy makes a call to an upstream, we can specify basically backup clusters. If things stop working to the main upstream that we're sending traffic to, we can actually send it to a backup cluster. And maybe this backup cluster, hint, hint, is actually a gateway running in a different cluster, in a totally different cluster. And so we can use two different Envoy upstreams, and when one of them starts to misbehave or fail, we can go to the backup. And so this lays the foundation for, number one, identifying when there are challenges in service-to-service communication within a single cluster. It lays the foundation for administrative control over how the traffic starts to fail over in bad scenarios. And it lays the groundwork for sophisticated, multi-network hops and using gateways as the router for traffic between networks. So again, I stress Envoy is a critical piece of the equation here. And any of the examples that we look at, today we'll look at examples based on Istio. That any of these examples that use Envoy, just keep in mind that when you start to do multi-cluster communication, Envoy has a lot more capability than maybe what your service mesh exposes. So the first pattern that we see, and then we'll try to tie back to the patterns that we saw earlier in a service mesh, and again, we're using Istio in this example. But the pattern is farther reaching than just Istio, is when we have multiple clusters on the same network, right? We can actually share a control plane for the service mesh, and we can let that service mesh take care, or that control plane take care of things like the service discovery and the population of the endpoints for any particular service. So when account tries to talk to user, the control plane will know, all right, well, I have user endpoints in this cluster, and I have user endpoints in another cluster. So let's present both of those to the through the control plane. And so in this case, across multiple clusters, we have the control plane living in one cluster. Service to service, there's not all that much to take into account because these are on the same flat network and they can just talk directly to each other. And they're sharing the same identity domain. They're sharing the same administrative domain. They're just doing it across multiple clusters. Now, some thoughts about this. It is, if you can do it, if you have a flat network, the simplest way to set up Istio and a service mesh in multi-cluster. There aren't any special Envoy routing rules. Maybe you're using zone-aware routing, but you're not using anything like the aggregated cluster or the locality-weighted load balancer or any of that kind of stuff. The shared control plane does increase your failure domain. So although you're using two different clusters, if the Istio control plane goes down, now you've affected both clusters. So you've merged these failure domains. If that's the case, then just make sure that that's you predetermined and you explicitly decided to do that. Another option is to use multiple clusters with a shared control plane. across different networks. So the networking is not shared, it's not flat, and the routing has to go through a gateway or an ingress point. So in this case, you have to set up Istio so that when it does its sidecar injection for either of these clusters, you have to identify that these are different networks. And you have to tell it what is the endpoint for the gateway in the other cluster. So you have to configure Istio to do that. So that when account service tries to talk to user, what it will see is all of the user endpoints, but it will now also see the endpoint for the gateway in cluster 2. So if things start to fail in cluster 1, when account is trying to talk to the user service, then it can start to fail over traffic to the user service in cluster 2. And that will go through the gateway. So Istio ends up using Envoy's locality weighted load balancing to do this in the Istio docs. Although more recently, I think I've seen it scrubbed of this term, but they were calling this a split horizon EDS, which means we'll prefer the local cluster for traffic first, but then if that starts to, those endpoints start to go away, then let's start to spill over into the endpoints that might be in a different cluster. Now this shared control plane across multiple clusters suffers the same drawback in terms of failure domain that the first pattern did as well when we shared the control plane across multiple networks or flat networks. Now, as we start to try to deal with these different constraints, so like in this case, we didn't have flat networking. We introduced two different networks. As we start to deal with these constraints like networks, like failure domains, we'll start to increase the number of moving pieces and the operational burden on the administrator. So we do have to label the networks. We have to make sure that the gateways, their endpoints are exposed correctly. And if they change somehow, that we have to update the Istio config and so forth. So there is some level of effort here to keep this thing operational. The last pattern that I'll talk about uses a separation of control planes across multiple clusters. So using Istio, when account wants to talk to user, we do still need to, either we'll talk locally to the user service, or if that starts to fail, we want to fail over to the user service in cluster 2. That traffic will go through the gateway for cluster 2, but the control planes are separate. So we're going to have to somehow tell the control plane of each of those clusters how to find services on the other cluster. And another thing that we're going to have to pay attention to is if these are two separate control planes, do they share the same identity domain? Can account in cluster 1 talk to user in cluster 2 and establish mutual TLS, propagate identity, and have it be trusted? So that's another thing that we're going to have to take into consideration. Either we're going to explicitly set up a separate identity domains, and we'll need some sort of exchange between the boundaries to establish trust, or we share a common root and the trust is established that way. Now in this particular model, if you're familiar with Istio, familiar with how this works, uses service entries to create the service discovery for one cluster to find the services running on another cluster. Now it's not as simple as just using service entries, and I'll talk about that in a second. But because we have separate control planes, now we're able to separate out our failure domains as well. If cluster 1 goes down, we're going to lose some of those applications, but cluster 2 and its service mesh isn't isn't affected. That continues to run. All right, so as we start going down this path, where now we have to somehow maintain the service discovery information, we have to solve for the identity problem, whether that's how are we going to allow communication and trust and encrypt that communication between the clusters. Now we also have another problem. Whereas in these scenarios where you had a single control plane, you could write the configuration for your service mesh, whether that's routing rules, access control, and so forth. You write that to the control plane. There's one control plane. In this case, now you have two or more, if you have more clusters. Now you have more control planes. Now you have to write configuration around, like I said, traffic routing and access control and so forth to each of the control planes that you might have in this multi-cluster setup. And not only that, you can't just replicate the settings out. These might not be homogeneous clusters. So you have to take into account that these are multiple clusters. Certain parts of the config needs to be federated and certain parts may not. So this has increased the burden on the operator to maintain the integrity of the system, to get it bootstrapped and then over the life of the system. So here's an example. When account wants to talk to user, it would probably use, it might not know or care about these other clusters that you have in your system. It will probably use the DNS name that Kubernetes offers for that service. In this case, it'd be something like users.default.svc.cluster.local, right? Now, we might have another service running in cluster 2, another user service. And in a failover situation, we might want to use Envoy's either locality weighted load balancing or aggregate cluster to service the traffic failover and to be smart about that. And so for account service to talk to user in another cluster, it needs to, that path between the two clusters needs to be opened up. And Istio, the only way Istio will know about services running in another cluster is if we explicitly tell it. So we create a service entry for another domain that represents the service running in a different cluster, and make that available to the routing rules that live in cluster 1. So now we can write rules and set up the load balancer correctly so that we can route traffic to cluster 2 on failover. Creating these service entries kind of looks like this. It's a YAML file where we have to specify things like the host name that we want to use. We have to specify things like the addresses that we want to use and the endpoints that we want to use. In this case, the service entry, the endpoints will end up being the gateway on cluster 2. And cluster 2's gateway will then know how to route the traffic to the correct user service. But we need to take into account things like, well, that addresses thing, what is that used for? And so in this particular example, in Istio, that addresses endpoint there, in this particular scenario is actually dummy addresses, but it has to be unique. So you have to somehow generate these IP addresses, keep them unique across your service entries. It's ultimately used so that when you try to resolve a DNS entry, it resolves to an IP address so you can continue, and then let Envoy do the routing control for you and ultimately route to the gateway. But these are the nuances of the service entry that you have to pay attention to. So again, coming back to the forces that we need to balance, we want security between our services. We want encryption between the services. We need to enable service discovery within our multi-cluster setup for the services that need to cross these boundaries. We need to be smart about how traffic fails over and how it starts to pick the correct and closest clusters where failover may be more appropriate than, let's say, going, crossing a zone might be fine, but crossing a region might not be ideal unless absolutely necessary. We want to be able to solve these problems across multiple networks. We want to isolate our fault domains, and we want to enable, once we start adding new clusters, to actually build for scale. But what about that extra burden for the operator? Now, this was the same exact problem that we saw in Kubefed. Kubefed, by creating this additional CRDs and trying to get the right clusters provisioned with the right services and so forth, Kubefed used a management plane to do that. And so at Solo, what we've been working on is building a management plane for Service Mesh that does exactly that, solving these difficult problems around service discovery, identity domains, and load balancing, and configuration, and so forth. So what Service Mesh Hub looks like is a very similar architecture to what we saw with Kubefed, but instead of driving the Kubernetes control planes, we're driving the Service Mesh control planes. And we're solving a lot of those challenges that we covered for you. So let's take just a really quick demo. How am I on time? Running out. Let me just do a quick demo. What we're going to look at in the demo is it's two different clusters, but the Service Mesh Hub management plane will be running on one of those two clusters. We'll have Istio installed on both of them, but we're going to actually run Service Mesh Hub on another one, or on one of those clusters. You could run it on a separate management plane. That's the ideal architecture, but for this demo, we'll just run it like this. So if we come back here and let's take a look at the abbreviated demo. First thing we're going to do is we're going to look at the two clusters that we have. We have on one cluster, the management plane context cluster, we have Istio 1.5 running. On the remote cluster, the second cluster, we also have Istio running, hopefully, if my network keeps up. If you're familiar with Istio, you should know that the book info demo is kind of the main demo that people use. For this demo, we have a product page service, which ends up calling details and ends up calling reviews. Now, in this case, we have two different versions of reviews on cluster 1. On cluster 2, we have even another version of reviews. So what we're going to do is we're going to install the Service Mesh Hub management plane. I'll give that a second. What that's going to do is set up all of the controllers necessary to be able to register these clusters, to be able to find the different service meshes and federate them. So we can see that our Service Mesh Hub installation worked out. If we run meshctl check, we should hopefully see everything installed correctly. And now what we want to do is register these clusters with the management plane. And so this is going to follow a very similar pattern to what Kubefed did, or any sort of multi-cluster management plane, what they do. And we're going to register cluster 2 with the Service Mesh Hub management plane. Depending on how long this takes, I can explain what it's doing pretty quick. Okay, so now we have these two different clusters. Let's see if they show up. Cluster 1 and cluster 2, excellent. Now that we've registered this with the management plane is going to go out and try to discover the service meshes that might be running in these clusters. So if I do get meshes on the management plane, we see that we have actually discovered, running in cluster 1 and cluster 2, two different Istio installations. Now, these are separate Istio installations at the moment. Let's see how easy it is to federate them. So the first thing that we want to point out is that these two clusters have different roots for their identity. And we can prove it or show it. When I make a call between reviews and ratings on cluster 1, we'll use a client to actually show the certificates. We can see that the root, so we see the leaf certificate, we see the root certificate ends with something 5xq. Let's see the same thing on cluster 2. We'll run the same command, reviews, calls, ratings, and we'll take a look at the root part of the certificate. That's different than what we saw on cluster 1. So these are two different identity domains. What we're going to do with Service Mesh Hub is we're going to create a CRD called the virtual mesh CRD. And with the virtual mesh, what we're going to say is federate these two meshes. And in this case, we're going to go with permissive mode, which just means federate all of the services from each of the clusters so that the services in cluster 1 can talk to the services in cluster 2 and vice versa. We're also going to specify that we want a shared root identity. And in this case, we'll have it auto-generate a root, but we could also point it to a specific one. We could tell Service Mesh Hub exactly which meshes we want to include in this virtual mesh, which ultimately then will be treated as a single global mesh. So let's go ahead and create that and cross our fingers. This is a live demo, even though you can obviously tell I have a script typing for me. So now if we get the virtual mesh, we should see in the status field that things have been processed and they're in an accepted state. So what's happened is we've created a new root CA, and we can take a look at that root CA. It's on the management plane cluster. And this ends with FA and some equal signs. What the remote clusters did, so the slides will show this. What the remote cluster did was generate their own intermediate CA and ask Service Mesh Hub to sign that with the shared root. Right, so we see the certificate signing request here. And we see the new CA certs, the intermediate ones that were created on the different clusters. We see that in cluster 1 and in cluster 2. And now what we want to do is we're going to recycle some of the workload pods here just real quick because we want them to pick up the new certificates with the same with the shared root faster than it would otherwise happen because we're on a demo and we're on a tight timeline here. Now, if we check the certificate chain, we should see that it terminates in the same root CA that we saw earlier. We see FA and the double equal signs. Now, if we do that again on the second cluster, we should see the exact same thing. So that means the identity has been established, the root identity has been established. And we see here, FA equals on the second cluster as well. So the demo keeps going. I can show, cross cluster traffic and so forth, but I do want to show service entries have been automatically created for us. So on cluster 1, the service entries have been created to be able to talk to the services running on cluster 2. So in this case, it would be reviews.default.cluster-2. And we've automatically taken care of the boilerplate stuff, mapping it to the correct gateway IPs and so forth. So what we've seen here is a few different patterns. As you start to go increasingly closer to your goals of failure domain isolation, solving for multiple networks, and cross-cluster traffic routing and failover, you see that there's additional burden, at least with some of the Service Mesh implementations today, that Service Mesh Hub is intended to solve. So we're getting here. I'm going to try to take a couple questions. I apologize, I didn't leave too much time. Please send your questions in anyway. Like I said, I plan on writing a blog on all this stuff in a lot more detail, and I can use that as an opportunity to address questions as well. Check out solo.io. We're working on a lot of cool stuff on Envoy-based stuff around service mesh, around API gateways, around WebAssembly. We just announced a developer portal for Istio, which gives a lightweight API management and developer API exposure for Istio. So absolutely just reach out. So let's see, we do have a couple of questions here, and I have a couple minutes. Let's see. When you say routing a gateway, it is natural to go to the HTTPS protocol and services. The same schemes are applicable to other protocols and
Yeah. Christian, there's one in here that says, you know, you had a lot of discussion on the application responsibility versus the infrastructure responsibility. And you listed like discovery, load balancing, and encryption as what are some other concerns that that Service Mesh can also unburden from code? Are there some additional ones that you can discuss?
Yeah, definitely. So that's a great question, because the Service Mesh does target and solve the types of networking challenges that are kind of ubiquitous across languages, across frameworks, and so forth. So I think, actually I have a slide here that touches on some of these things. Envoy. So there are things like, and it's not just about the implementation, it's about keeping it consistent, right? Things like timeouts and retries, circuit breaking, retry budgets, failover, traffic routing, so forth. These are things that, yeah, you can implement that in your application code. And in fact, a lot of us did this back in the day. Either we wrote our own libraries for this, or we used something like Netflix OSS or Finagle or something like that. The challenge then becomes when you start introducing multiple languages, multiple frameworks into your microservices deployments, and having to solve those same problems over and over in different languages. Some might be based on blocking, or some might be based on non-blocking reactive frameworks and so forth. The implementations for them are not going to be exactly the same. Even if you could possibly cover all of the pieces of functionality, you pull things off of NPM or pip if you're on Python, and Maven if you're in Java, and all of these implementations are slightly different. And when you start dealing with distributed systems and you can't reason about exactly what the behavior is supposed to be, even across these different languages, that ends up being, you know, a huge stumbling block in debugging when things go wrong. So keeping the consistency of these networking related pieces of functionality between services is key. And of course, as you start to scale out to multiple clusters and multiple clouds and so forth, then it's even more important. So I see we are a bit
over time. One thing we could do is we can have a follow-up session just on some Service Mesh Q&A, and we can also answer some of these Q&As directly in a blog post.
Yes.
And folks, if you have more, or if there's specific topics that things that Christian touched on here that you would like a deeper dive on, please hop into our slack.solo.io, and you can DM myself or Christian